All right, welcome to Unit 4 on probability, random variables, and probability distributions. In this video, we are going to talk about topic 4.9, transforming and combining random variables. All right, first let's make sure we understand the difference between what I mean by transforming versus combining. When I talk about transforming, we're taking a single random variable and converting it to a new unit or adding or subtracting a constant. So an example here could be if W is the random variable for the weight of something in pounds, but instead of pounds, we just want to convert it to kilograms. That's a transformation. Or if S is the number of t-shirts we sold, but we want to convert that to how much money we made off of selling our t-shirts, that's just taking the number of t-shirts we sell and converting it to dollars. Or if L is the length of a table, the length of a table could vary. Some tables are longer than others. But I want to add 2 inches to all possible outcomes. All I'm doing is adding 2 to that random variable. Now, combining is a little bit different. Combining is one of 2 things. It's taking a single random variable, but repeating it multiple times. Or adding or subtracting 2 different random variables together. So an example would be if M is how many letters are in your mailbox in 1 day. But now we want to look at how many letters are in the mailbox over 7 days. So M is how many letters are in your mailbox on any single day. But now we want to repeat that random event and look at letters over the course of 7 days. So I'm repeating that random variable. I'm combining 7 days of that random variable together. A different example could be if D is how many dogs a family has. C is how many cats a family has. But we want to add those together. We want to look at T, the total of cats and dogs that a family has. So in that case, we're adding 2 different random variables together. So transforming is more about converting or just adding a constant, versus combining is really more about repeating a random variable or combining 2 random variables together. Let's talk about transforming first, because to be honest, it is quite easy. All right, there are 2 different things you have to be concerned about. If you're multiplying a random variable by a constant. So if you're taking a random variable and you're just multiplying it by a constant in terms of maybe like converting. If you're going to convert to one unit from another, you typically have to multiply. So if you have your original mean as mu, then the new mean is simply A times mu. Multiplication affects mean. That's easy. We've actually covered that way back in Unit 2. Original standard deviation is sigma, and the new standard deviation would be A times sigma. So basically, multiplication of a constant affects both the mean and the standard deviation by just multiplied by that constant. However, if you're adding or subtracting a constant, okay, you're adding or subtracting a random variable by a constant. Here, it's important to note that addition or subtraction of a constant does not impact standard deviation. So for example, if we're going to add or subtract a constant A, the mean will go up or down by that constant A. So if the original mean is mu, then the new mean is simply mu plus or minus A. If you're adding, add A. If you're subtracting, subtract A. But standard deviation remains unchanged. So adding or subtracting does not change the standard deviation. Again, this is a topic we've actually already covered. So your old standard deviation and your new standard deviation will be exactly the same. It would not impact it at all. All right, let's look at some examples to see how easy this is, because I truly believe this is simple. All right, so let's say that the mean and standard deviation for how much weight an Olympic lifter can clean and jerk is a mean of 147.27 kilograms with a standard deviation of 15.83 kilograms. So let's just say that we have weight, W. How much weight can an Olympic lifter lift? Well, the mean of W is 147.27 kilograms, and the standard deviation of W is 15.83 kilograms. So again, what this means is that in the long run, if I were to look at a large number of Olympic lifters, they would average 147.2 kilograms. But they would vary on average by about 15.83 kilograms from the mean. But the question I'm going to ask you is, what would the mean and standard deviation be if we wanted to convert to pounds? Well, how to convert to pounds is we need to use a conversion factor. 1 kilogram is equal to 2.2 pounds. So if all I want to do is convert to pounds, I have to multiply the kilograms by 2.2. It's that simple. So if I have my mean and I want it in pounds, all I got to do is take my old mean and multiply it by 2.2. That will give me my new mean because I'm just transforming. My standard deviation, well, multiplication affects standard deviation as well. So my standard deviation would be 15.83. but times it by 2.2. Again, all I'm doing is I'm converting here, right? I was in kilograms, but now I'm going to use the conversion factor that 1 kilogram is equal to 2.2 pounds. So by multiplying, the kilograms cancel and I get pounds. And the same thing is true for standard deviation as well. So all I got to do is grab a calculator, 147.27 times 2.2 converts that to 323.99 pounds. So almost 324 pounds. Taking 15.83 times it by 2.2, we get 34.83 pounds. So again, this is like chemistry class. I'm just converting. I'm just, canceling out my kilograms to get the pounds. Just multiplication. Easy. Multiplication affects mean and standard deviation. Let's look at a second example here. The following probability distribution represents S, the number of sweatshirts that Mike sells per day. Mike could sell 10, 11, 12, 13, 14, or 15 sweatshirts in a day, and the probabilities are there. Now, I actually went ahead, and I was a nice guy, and I thought I was being nice. I went ahead and actually calculated the mean and the standard deviation for you. Now, I hope you remember how to do it. You could certainly use your calculator or you could use the formulas, but I went ahead for you just to save you some time. And the average number of t-shirts that Mike sells is 12.1 over the long run with a standard deviation of 1.41. The question is, if he sells his sweatshirts for $27 a piece, what is the mean and the standard deviation of his daily sales? So all we're doing is saying that each sweatshirt, if sold, costs $27. So we're just converting here, right? So the mean of the sales would be saying, well, listen, I expect to sell 12.1 sweatshirts, and every one of those sweatshirts costs $27. So 12.1 times 27 is an expectation that on a daily basis, Mike is going to sell $326.70 worth of sweatshirts. Again, just converting from a number of sweatshirts to the amount of money that that number would be worth. And the same thing would be true for the standard deviation, which is also affected by multiplication. So I take the 1.41 and I'd also multiply that by $27. 1.41 times 27 is $38.07. So in the long run, after selling many days worth of sweatshirts, I keep wanting to say t-shirts, sorry, of selling sweatshirts, in the long run, Mike would expect a daily sales of $326.70, but that would vary on average by $38.07 from the mean. Pretty easy. Let's look at a third example. All right, same exact example. Sweatshirts, sales, we get it. Now, if he sells the sweatshirts for $27 a piece, and he takes into account the expenses. I mean, he has to spend money on buying the sweatshirts, maybe the ink to put a design on them. He has to pay his employees who actually do the selling of them. So there's some expenses involved as well. So Mike's revenue is going to be a combination of how much he makes per sweatshirt minus $8.50. That is the expense that goes into the sweatshirts. So what is the mean and the standard deviation for his revenue? Well, he's expected to sell 12.1 sweatshirts per day times $27 per sweatshirt. But then I got to subtract that $8.50 revenue that does go into the daily, paying the employees, keeping the electricity on, all that kind of stuff for his store. But that's just a subtraction of a constant. So again, take the mean, 12.1, times it by the 27. That's the $326.70 that we saw in the last problem. But now we have to subtract away the expenses to get how much money Mike actually keeps. And that is $300.18. I'm sorry, $318.20. Sorry, I read that wrong. Now, what about the standard deviation? Well, if we take the 1.41, that's the standard deviation for the sweatshirts he sells. Each sweatshirt is costing $27. But remember, subtraction nor addition affects standard deviation. So by thinking about that expense, $8.50, that will only impact the average. That's not going to impact the spread around that average. So I don't subtract the $8.50 at all. I just do the 1.41 times 27, which is again $38.07. So this is important to note, that rule that we talked about here at the very bottom, that multiplication affects everybody, but addition or subtraction of a constant only affect the mean. So that is why I did not subtract the $8.50 that is due to expenses. I only did that for the mean. So again, pretty easy. Let's do one more example. This is kind of a generic one, which you'll typically see on an AP test. All right, the mean and standard deviation of a random variable, x, I have no idea what it is, but the mean and standard deviation are 5.6 and 1.24. So a new random variable is described as 8x plus 4. So it's y equals 8x plus 4. So what is the new mean and the new standard deviation for y? Well, again, multiplication and addition both affect mean. So I'm going to take 8 times my old mean of x, and I'm going to add the 4 to get my new mean. 8 times 5.6 plus 4 is 48.8. Now, this problem has no context to it, so I don't know what the units are on this, but that's the mean. So again, that's because the mean is affected by both multiplication and the addition of a constant. But the standard deviation, however, is only going to be impacted by that multiplication. The addition, moving data up or moving data down, moving out comes up, moving out comes down, that's not going to affect how spread out the data is. So I'm just going to simply take 8 times 1.24, and I get 9.92. So this is a very common type of AP question to just make sure that you don't get tricked and you don't accidentally add or subtract a constant to a standard deviation, because it does not affect it. All right, let's now switch gears to talk about combining. So please remember, when repeating a random variable or combining two or more random variables together, we need to once again consider how the mean and the standard deviation get affected. All right, so keep in mind, I have to once again explain, just so you know, that what does combining mean? Combining means repeating a random process multiple times or combining two random variables together. So here's an example. If Mike were to examine 5 days of selling sweatshirts, not one day, but if he were to say, what do I expect over the course of 5 days? That is simply taking his random variable S and repeating it 5 times. But maybe Mike also sells sweatpants, and that's P. Well, now we want to combine the total amount of clothing items. So we want to combine the sweatshirts with the pants to see. Or maybe we want to look at the difference between the sweatshirts and pants. But the idea is now we have two random variables. How many sweatshirts do I sell? How many pants do I sell? And we want to put them together. All right. First and foremost, this is so important. In order to combine random variables in either way, repeating or combining two random variables together, they have to be independent of each other. The random variables themselves, or maybe 2 or 3 different random variables, they have to be independent of each other. This should make complete sense, because if there was no independence, if one event's outcome did impact the next event's outcome, then we would have a whole mess, because the probabilities would not stay the same. Each outcome's probability would change, and then all of a sudden combining is very difficult. So please make sure for every combining problem, we have to either assume that the variables are independent of each other, or we have to literally be told that. All right, so let's talk about the rules. First, let's talk about how combining random variables affects means. This is pretty easy or straightforward. If you're going to repeat a random variable multiple times, you simply take the mean multiple times. So you have the random variable the first time, then you have it again, and then you have it again, and then you have it again. So if you're going to repeat a random variable 4 times, if I'm going to sell sweatshirts for 4 days, then I'm just going to look at each day's expected value, add them together. Now, again, as long as it's the same each day, you could make that a little bit faster by using multiplication. But if you're going to add 2 different random variables together, well, it's pretty easy. Take the mean for X and add it to the mean for Y. I mean, it doesn't get much easier than that. If you're going to subtract to look at the difference between how many sweatpants and how many sweatshirts I sell, well, then I simply take the mean for X and I subtract the mean for Y. I mean, it's really straightforward. So when you're combining random variables, considering how the mean is impacted is very simple. It's not difficult at all. It just takes some common sense. However, when we're combining random variables, thinking about standard deviation, this is a little tricky. This is definitely a little bit tougher. And I'll be honest, some kids totally understand this. They get it. Other kids just, it kind of goes over their head a little bit. But at the end of the day, you got to follow the rules. And even if you don't quite understand it all, understand the rules and follow the rules, and you should still get the problems correct. All right, the very simple fact is this. We cannot add standard deviation together, nor could we subtract. So we cannot add, we cannot subtract standard deviations together. We can do means. Look, go back to this page. We can definitely add means together. That's not impossible, but it is impossible to add standard deviations. You could only add variance. And notice that you can't even subtract variance. You could only add variance. So I'll explain a little bit more of what I'm saying here as best I can. All right, first, recall what variance is. Variance is the value inside the square root before the square root is taken. So if you remember, we actually recently went over this. The standard deviation is equal to the square root of variance. So that implies, if you square both sides, simple algebra, that standard deviation squared is equal to variance. So these two things work interchangeably. Standard deviation is the square root of variance, or standard deviation squared is equal to variance. It's simple algebra. So to combine random variables, we have to think about combining their variance first. So basically, we must combine all the variance together. Then, once all the variance is combined, we could take the square root of the variance, because the square root of variance is how you get back to standard deviation. So that's what you need to memorize. The idea is that we cannot add or subtract standard deviations. Don't you ever dare take two standard deviations and add them together. Never, ever, ever. You have to add their variance. So here's the rules. Right? If you're going to repeat a random variable 4 times, okay, what you have to do is you have to take the variance, which is the standard deviation squared, plus the variance, which is the standard deviation squared, plus the variance, which is the standard deviation squared, plus the variance, which is the standard deviation squared. So you have to add up all that variance. Because remember, when you square standard deviation, you have variance. So this number right here is variance. This is more variance. This is more variance. This is more variance. In fact, this is 4 variances added together. Once you add all that together, you take the square root, because that's how you get back to standard deviation. Now, one thing you can do to speed this up is you could take your variance and times it by 4, because you have 4 variances, and then take the square root of that. Now, let's take a quick pause right now, because I cannot tell you how many kids will say, wait a minute, if I have m squared plus m squared in a square root, isn't that the same thing as just m plus m? Oh my gosh, pay attention in algebra class. Absolutely not, right? A square root does not cancel out squares if there is a plus sign in between them. So please do not ever think that. You need to go back to algebra class. All right, now if you're adding 2 different random variables together, what you do is you got to take the variance for x, which is standard deviation squared, take the variance for y, which is standard deviation squared, add up all of that variance, and then take a giant square root to get back to standard deviation. So remember, sigma is standard deviation. If I square it, I got variance. So it's that easy. But this is also super important for you to pay attention to. Variance always builds. So even if you are subtracting 2 random variables together, you still add their variance. This is super important. So even if you are looking at the difference between x and y, like, hey, what's the difference between the pants and the sweatshirts? You still add variance. Variance can only add. When you combine 2 random variables together, whether you're adding them or subtracting them, you're still putting them together, so variance always adds. This is what I'm talking about. Some kids don't understand that. Well, I hope you do, but if you don't, you got to memorize it. All right, let's look at some examples. What is the mean and standard deviation for how much an Olympic lifter can lift is 147.27 kilograms and 15.38 kilograms. All right, we already saw this problem, but this time we're going to look at a team. A team consists of 6 lifters. What would the total mean and the total standard deviation be for the team? So what's the total mean for the team? Well, just walk through it, right? The mean is easy. The first lifter is supposed to lift 147.27 pounds, or kilograms. So sorry. The second lifter is supposed to lift 147.27 kilograms. the third lifter, the fourth lifter, the fifth lifter, and finally, the sixth lifter. I would expect every one of my 6 lifters to lift 147.27 kilograms. Why? Because that's what's expected in the long run. Now, obviously, I would speed this up by just doing 6 times 147.27. But I can't emphasize this enough. Guys, this is not transforming. This 6 is not a constant. I'm not multiplying by 6 to convert. I'm multiplying by 6 to represent 6 different lifters. So to be honest, I actually would prefer, I'm not telling you that you have to do it this way, but I would prefer that you write it out because you actually can see each of the 6 lifters. But multiplying is a faster way to get the answer. So 6 times 147.27 is 883.62 kilograms. So if I have 6 lifters on my team, I would expect them to lift a grand total of 883.62 kilograms. All right, but that number is going to vary, right? Because not every lifter is going to be exactly the same, so the total is probably going to be a little bit of variation. That's where standard deviation comes in. So first, I cannot do what I just did for mean. My gosh, that's what I'm trying to explain to you. I cannot take 15.83 plus 15.83 because you're not allowed to add standard deviation. So what I have to do is I have to take 15.83 and I have to square it because now that is variance. Now, honestly, don't even do it. Don't literally square 15.83. Just write down 15.83 squared. We're going to let the calculator do all the heavy lifting anyway, but I'm just understanding that the moment I put a square on that number, now it's variance. Then I have the variance for my second lifter, plus the variance for my third lifter, plus the variance, and I'm sorry for my crappy handwriting, the variance for the fourth lifter, plus the variance for my fifth lifter, plus the variance for my sixth lifter. I have 6 lifters worth of variance, and then I'm going to put a giant square root around all of that variance to get back to a standard deviation. Now again, you can speed this process up by saying, listen, I got 15.83 squared. That's my variance. And I got 6 of those variances. But again, I'm not multiplying by a constant here. I'm multiplying by 6 to represent the 6 lifters. And then I'm going to put a square root around all of that to get my standard deviation. So the square root of 15.83 squared times 6, just make sure that 6 is inside the square root. And I get 38.78. 38.78 kilograms. All right, guys, so please make sure you truly understand how to do the standard deviation. All right, let's talk about Mike again, selling his sweatshirts. Once again, Mike has an average of 12.1 sweatshirts per day, 1.41 standard deviation. All right, over the course of 5 days, how many total sweatshirts do you expect Mike to sell? Well, how many total sweatshirts? Well, again, that's 12.1 for the first day, 12.1, 12.1, 12.1. So I'm just going to speed this up. It's 12.1 for the 5 days. Again, that's not a constant. That's just me multiplying by 5 for each of the 5 days. And that means he expects to sell 60.5 sweatshirts over the course of 5 days. What about the standard deviation? Please do not do 1.41 plus 1.41, or do not do 1.41 times 5, because remember, addition is repeated, multiplication is repeated addition. You're not allowed to add standard deviations. So what I have to do is I got to take the 1.41 squared. There's my variance. Again, don't actually square it, just put a square on it. Now you got variance. And then I got 5 days worth of variance. I got 1.41 squared for the first day, 1.41 squared for the second day, all the way down the line. And then I need a giant square root around all of that variance to get back to a standard deviation. So again, that's going to be the square root of 1.41 squared times 5. Make sure that 5 is in the square root, please. And I get 3.15. So over the course of 5 days, Mike expects to sell 60.5 sweatshirts, but it could vary a little bit more, and that number is the 3.15. All right, let's look at another problem here with Mike. So let's talk about Mike. We already know that the mean of his sweatshirts is 12.1. The standard deviation of his sweatshirts is 1.41. But let's introduce P, sweatpants. Mike also sells sweatpants. Now, I'm not going to waste my time giving you a probability model. I'm just going to tell you. He sells an average of 8.5 sweatpants per day. So not quite as many. More people buy sweatshirts, come on. And with a standard deviation of 2.4. So what is the expected total amount of sweatshirts that Mike sells? Sweatshirts and sweatpants. So here I'm combining two different random variables together. Well, it's easy. 12.1 sweatshirts plus 8.5 sweatpants. I mean, my goodness, this couldn't get easier. So he expects to sell 20.6 total articles of clothing. What about the standard deviation? Don't you dare add 1.41 and 2.4. You're not allowed to add standard deviations. I have to take the variance for his sweatshirts plus the variance for his sweatpants. And again, don't actually square them. Just put the square there. The calculator is going to do the hard work. You're just squaring it to show that it's variance. And then put a giant square root around all of that to get back to a standard deviation. So that's the square root of 1.41 plus 2.4, 1.41 squared, plus 2.4 squared. I'm doing this on my calculator right now, and I'm just trying to make sure I got it down right. And again, some kids, they don't want to type it in right. They want to mess it up. So just be very careful. That's what I'm saying. Don't actually square it. Just put it in your calculator as squared. And don't forget the square root goes around everything, and we get 2.78. And again, I really encourage you, grab your calculator, pause the video. Just make sure you know how to type this into your calculator to get it as well. So this would be 20.6 total sweatshirts and sweatpants with a standard deviation, because some days he might sell more, some days he might sell less. So the total standard deviation is 2.78. All right, another question then with Mike. What is the difference in his sweatshirts and sweatpants? What's the difference, right? So now I'm talking about the difference. So what is his average difference? Well, this is easy, right? We expect to sell 12.1 sweatshirts minus 8.5 sweatpants, 12.1 minus 8.5. So we expect there to be a difference of 3.6, right? Like we expect 3.6 more sweatshirts. I mean, that's just common sense, right? I mean, 12.1 sweatshirts, 8.5 sweatpants. So obviously we expect more sweatshirts, 3.6 more. But that difference could vary. Like some days he could sell slightly less sweatshirts, slightly more sweatpants. So the difference is a random variable, right? Just like the total is a random variable. Some days he might sell more of both. Some days he might sell less of both. But again, the numbers could vary. So it's not always going to be 3.6. Could be a little more, could be a little bit less. And that's where standard deviation comes in. But this is what's really important. You can't add standard deviations. You can't subtract them. You can only work with variance. So 1.41 squared is the variance for the sweatshirts. 2.4 squared is the variance for the sweatpants. But even though the question is focusing on the difference, I still add my variance because no matter what, I'm taking these two things and I'm looking at them together. Whether I'm subtracting them or adding them, I'm still bringing them together. So variance always builds. So your variance is going to always add. So it's the same variance we got in the previous problem, 2.78. That is really, really important. That's a tough question that they'll try to trick you on the AP stats test. So don't get tricked by that. All right, here's a very generic example that you will also typically see on the AP stats test. All right, we have a random variable x, means 135, standard deviation 17. Got a random variable y, means 105, standard deviation 8. And now they want us to find the mean and standard deviation. Well, actually, I take that back. This just wants us to find the standard deviation for x minus y. So the standard deviation for x minus y is going to be, oh boy, what most kids do is they'll do 17 minus 8. Gosh, that's going to get you the wrong answer. Some kids will do 17 plus 8. That's going to get you the wrong answer. You got to do 17 squared. That's the variance for x. Plus 8 squared. That's the variance for y. And then square root all that. Yes, I know I'm looking at the difference, but remember, when you're looking at the difference, you're still bringing these two variables together. Variance always builds. And please don't ever waste your time actually calculating 17 squared. Just write 17 squared. You know that represents variance. All right, so I get a total standard deviation of 18.79. Awesome, easy. Now again, remember, I mentioned this. They have to be independent. So when we talk about sweatshirts and sweatpants, they have to be independent. So this is something I just assumed. Like, why would me selling more sweatshirts impact sweatpants? I don't know. I mean, you could come up with a million reasons why maybe it does, but if you're going to do everything I've been showing you in this video, you just have to assume that the variables are independent of each other. All right. Now, the one last thing I want to talk about is what about shape? Like we've talked about that discrete random variables can be skewed left, they can be skewed right, they can be normal-ish and so forth. Then it's important to note that when you combine random variables together, it does not change the shape. So if you're normal prior and then you transform, say, to pounds, like so, go back to my lifters. Like if the distribution of my lifters followed a normal model and I go from kilograms to pounds, it's still going to follow a normal model. If my sweatshirt sales are skewed right, well, if I look at 5 days versus 10 days versus 1 day, it's still going to be skewed right. So shape does not change. All right, so let's put all this together for one more final problem. I know this has been a long video, but there's a lot of good content here. All right, Katie owns a gift shop, or a gift, God, I really have a hard time spelling. Katie owns a gift shop. And I don't even try to rush, and I try to take my time. I still have typos. All right, Katie owns a gift shop that sells baskets with fruit. So the mean and standard deviation of the weights of apples, pears, and the basket are below. So the average apple's 4.72, but it does deviate by 0.2, like you get it, right? Mean and standard deviation for apples, mean and standard deviation for pears, mean and standard deviation for the basket. And it does say that they follow an approximate normal distribution. So apples follow a normal distribution, so do pears, so does the basket. All right, the question says, what is the mean and the standard deviation for the total weight of a basket with 5 apples and 3 pears? So we got 5 apples, 3 pears, and we do have 1 basket, right? There's still the basket that these things are in. All right, so what about the mean? What about the mean for the total? Well, I have 5 apples, so I got 4.72 plus 4.72 plus 4.72 plus 4.72 plus 4.72. I'm just going to do 4.72 times 5 to speed that up. But again, that 5 is not a constant. It's just representing the 5 apples. And again, if you want to write out 4.72 5 times, please feel free. Then I'm going to add in the 3 pairs. So I got 5.41, another 5.41, another 5.41. So I'm just going to multiply that by 3 for the 3 pairs. And then I just have 1 basket, so I'm just going to be adding into the mix the fact that the basket weighs 13.25 ounces on average. So again, 4.72 times 5 plus 5.41 times 3, my 3 pairs, plus the basket, 13.25, and this gets you 53.08. So if she were to throw 5 apples, 3 pears into a basket, she is, well, why did I put a dollar sign there? I need to really slow down here. She would expect that basket with 5 apples and 3 pears to weigh 53.08 ounces on average. Obviously, sometimes that basket could be more, sometimes that basket could be less. So of course, there's a standard deviation that comes in as well. Now, once again, I need to work with variance. So the variance for 1 apple is 0.2 squared. But I got 5 apples, so I got 0.2 squared, 0.2 squared, 0.2 squared, 0.2 squared, 0.2 squared, multiplied by 5 to make it a little bit easier. Then I have 0.18 squared. That's the variance for a pair. And I got 3 pairs. So I got 0.18 squared, 0.18 squared, 0.18 squared for my 3 pairs. And then I got the basket, which is 1.88 squared. So I can only combine variance. So I got 5 apples of variance, 3 pairs of variance, 1 basket of variance. And then I need to put a giant square root around all of that to get my grand total back to standard deviation. So just make sure that when you type this in, it's all inside the square root. One common mistake kids will do is they'll square the 5. No, don't square the 5. The 5 is just representing that you have 0.2 squared 5 times. Then I got 0.18 squared times 3, and then I got the 1.88 squared. That's my basket. That's the variance of my basket. So I end up getting 1.96. So 1.96 ounces is what my standard deviation will be. So remember, these numbers represent the fact that if I had many baskets of 5 apples, 3 pears, then I would expect the total average to be 53.08 ounces. But some baskets, because apples, pears, and the basket all vary, some baskets could be heavier, some baskets could be lighter, and that's where the standard deviation comes in as well. All right, guys, hopefully you learned a lot in this video. It's actually not a ton of content. We just did a ton of examples because I really wanted to kind of hit home the points. But go back and look at the key parts that talk about the formulas and how to actually combine this stuff. But I can't say enough times, you cannot add or subtract standard deviation. You could only add variance. All right, guys, tough video. Please make sure you pay attention and be ready.